All right, thanks. Thanks for a little patience, everyone, and welcome to today's webinar. Before we start, I just want to remind you regarding our housekeeping rules. So if you join or when you join, please take care that your microphone is muted and that your camera is turned off, so the presentation can run as smoothly as possible. Secondly, if you have any questions regarding the presentation and for the speaker, feel free to drop them in the chat box, or if you feel confident or if your connection enables this, just raise your virtual hand and we will ask you to ask your question live after the presentation. I'm extremely happy to have Tom Rowland today as a speaker for the webinar. He's a PhD candidate at the University of Lincoln. His supervisors are Oliver Burman and Tom Pike, and he's going to talk today about the network perspective on animal behavior and welfare. And I think we are all extremely curious about that topic. And without further ado, Tom, feel free to start your recording.
Sure. Okay, I'll just start it now.
Hello, my name is Tom Rowland. I'm a PhD student at the University of Lincoln in the Animal Behaviour, Cognition and Welfare Research Group. And I'm going to be talking today about this network perspective on animal behaviour and welfare. So today we're going to just a bit of an overview. I'm going to start by discussing some recent insights from human psychiatry and psychology on what the nature of psychological constructs are and different perspectives on this. And then kind of move on to discuss whether these ideas are relevant to animal behaviour and welfare. And after sort of concluding that I think they are, well, I'll talk about some of the implications and applications of these ideas with an empirical example in the context of pain and behaviour in companion dogs. And then I'll end by just discussing some possible future directions. So to start with, psychological constructs have typically been conceptualized as these latent variables. So if we think of this in terms of depression, let's use that as our example. So under a traditional psychological view, depression is a latent variable, and latent variable, is typically basically just something we can't measure. It's our theoretical construct of interest. And let's say we'll use a simplified example where we've got these 4 symptoms of depression. And we know that these 4 symptoms tend to co-occur together. Now, from a latent variable perspective, the explanation for why these 4 symptoms tend to co-occur is because they share a common cause. So they are caused by this latent variable, which we can't directly measure, but we see the arrows kind of pointing from this central variable out to each symptom. And once we take into account the common cause, we don't see any connection between the symptoms themselves, the measurable symptoms themselves. We just, they are independent once we take into account the depression central variable. In the last sort of 10 years, this alternative perspective or approach has been promoted, called the network approach to psychopathology, or the network theory of psychopathology. And basically what it says is that there's no reason to invoke this concept of a latent variable. We don't need it to explain the covariation in the symptoms we see. So if you notice in this diagram, there is no longer the central variable of depression. It's disappeared, it's out of the picture, we don't assume it exists. But we're still left with the 4 measurable symptoms, and we see lines connecting the symptoms. So the basic premise here is that the reason the symptoms tend to co-occur together is because they directly cause each other. You know, there's these feedback loops and direct interactions between the symptoms. And in this sense, depression isn't a latent variable causing the symptoms. Depression is simply the symptom network. So if you think about this, if we started this trouble sleeping symptom, then let's say you have trouble sleeping, then the next day you might feel a bit fatigued. Because you feel fatigued, you might have difficulty concentrating, maybe because you've had difficulty concentrating and you haven't got much work done, that affects your mood, and because you're feeling a bit lower, you have trouble sleeping, and you end up in this sort of vicious cycle where the symptoms maintain themselves. And that's essentially what the network theory of psychopathology is. It's about these vicious cycles and interactions between symptoms that, you know, transition people into these stable states of symptom interactions maintaining each other. So within human psychology, this network approach hasn't only been applied to psychopathology, it's been applied to lots of different psychological constructs. So this is just a few examples. So we've got sort of attitude here, attitude networks, intelligence, which is actually probably where this idea first originated. There's been some recent work on emotion, you know, interaction between components of emotion, which might be a particularly relevant sort of area and application for animal welfare. And it's also been looked at in personality, where, you know, these common personality dimensional models, like the Big Five, it's argued that, you know, these dimensions can emerge through direct interactions between the individual components. We don't necessarily have to assume that there is this latent variable of, for example, neuroticism, that, you know, that it exists somewhere. So it's been applied to lots of different situations. I'm not going to spend too long talking about this, but it's worth mentioning because the first sort of paper or application of this network approach in non-human animals, to my knowledge at least, is this paper by Gould in 2016, where he looked at dog personality as a network in patrol dogs and detection dogs. And the results kind of suggest that perhaps this playfulness variable was potentially particularly important for success in both types of roles. I'm not going to talk about that in more detail because I'm going to focus more on the animal welfare setting today, but I thought it was worth mentioning, and it's worth having a look at that paper if any of this interests you. So, thinking about animal welfare, are we dealing with latent variable systems or network systems? So, do the same ideas that have been developed in psychiatry and psychology also apply to animal welfare? And traditionally, how we're kind of all familiar with thinking about welfare, we basically try to triangulate behavioral, physiological, and cognitive lines of evidence to infer something about the welfare of an animal or group of animals. However, it's potentially less kind of discuss specifically what sort of framework or model we're working with. So, you know, I would kind of argue that the traditional approach implies we're dealing with a latent variable, although, at least to my knowledge, it's rarely theoretically framed that way and, you know, not formally statistically modeled that way. So perhaps there's a bit of a gap for, you know, formalizing exactly what sort of systems we're working with in animal welfare. And, you know, that forces us to confront this problem of, are we dealing with latent variables, or are we dealing with variables that simply might causally interact with each other and have their own kind of independent causal power? So this can be represented in this diagram here. In A, on the left here, this is kind of sort of welfare as a latent variable, and we see that this model assumes that changes in welfare state directly cause the changes in the measurable realms that we typically look at. So changes in welfare cause changes in behavior, physiology, and cognition. But that's not necessarily true. Maybe welfare subjective states emerge out of causal interactions between all these different sort of interacting components. And that's essentially what the network theory, if you like, of animal welfare is that the things that we're measuring might have their own causal autonomy. So it's probably easier to think about an example. So if we think about, let's say we measure 3 classical, traditional welfare measures. So if we look at fearful posturing, low appetite, and body condition score. So I typically think in terms of dogs because that's what I know best. But this example, if it helps to think in terms of specific species, you can think of it however you like, whatever species you want. These are probably 3 measures that apply to any species. So the latent variable model of these 3 measures would imply that changes in the welfare of the animal are what cause the scores in the measures. So they cause the fearful posturing, the changes in appetite, and the body condition score. And once we take into account that latent variable, these measures are independent. The network approach would say we don't necessarily need the latent variable, we don't need to assume it exists. Instead, what if these variables directly interact with each other? So this would say that if an animal shows fearful posturing, this leads to directly causes low appetite, which leads to directly causes low body condition score. And at least to me, this makes more intuitive sense. If an animal, senses threat, then feeding is not a priority, so we'll see a reduction in appetite. And if a reduction in appetite persists over time, if they're exposed to the environment where they perceive threat regularly, then that will lead to low body condition score due to less calories consumed. So that's all well and good, but what are the implications of this? So one of the big implications is that it means individual components are not interchangeable. Like I sort of mentioned, every variable we measure is potentially has its own causal power. It also means that the dynamics of how things change over time and how we control network systems is very different. So interventions have to take place at the level of the variables and their interactions and not at the level of latent variables. And I'll come on to an example of that in a second. It also means that a lot of the phenomena we experience or measure might emerge. They aren't real entities that we need to go and search for. So, this has research implications. We might use different models. We might interpret data differently, maybe design our experiments slightly differently. Maybe we don't need to do experiments that go out searching for the existence or the cause of neuroticism because it doesn't actually exist. So essentially, it can kind of be summarized in the sense of, in order to understand, predict, and control behavioral systems, the complex dynamics of the systems need to be studied. So thinking about these implications in a little bit more detail, using the example we just spoke through, the same 3 welfare measures, if I am dealing with a latent variable system, and I want to improve scores on the 3 variables that I've measured, then to do that, I need to intervene at the level of the latent variable. I need to intervene at the level of the cause. So if I did something that just, tweaked or manipulated a single variable, then I wouldn't expect any changes in the rest of the system because there's no connection. If I change this variable here, then appetite and body condition score wouldn't change because there's no connections in this model. Everything is due to this common cause, this latent variable. However, in the network system, if I intervene at the level of a single variable, so I manage to tweak this animal's threat perception and change their fearful posturing, then that would predict that I would see improvements in appetite and improvements in body condition score. If I just kind of change appetite by, I don't know, let's say there's some medication or chemical means of improving appetite, then I might see an improvement in body condition score, but I wouldn't see an improvement in fearful posturing. So the two models make very different predictions, and this has implications for how we intervene and control work. So with this idea of interventions in mind, that raises the question of what we should intervene on, or how do we select what we intervene on. One idea in the human literature has been kind of dubbed the centrality hypothesis. And the basic idea is that certain nodes, so I'll come on to terminology in a second, but nodes are basically the things we measure, have more influence than other things we measure. And it would make sense to try and specifically target and alter these influential nodes to produce the largest effect on the overall network. And without going into too much detail, because there's lots of sort of debates about what the best measures of influence are, what sort of statistical metrics of networks we should use to infer what's important in the network. For the sake of this example, just assume that we can do that. And a potentially useful little analogy is probably not strictly directly applicable, but it might help to think about it. If you think about it in terms of UK railway networks, right? So if there's a signal failure at a tiny station at the edge of the country that has just a single connection to another local station, that's probably not going to have a huge effect, propagate throughout the rest of the UK rail network. However, if there is a signal failure at a large London station that is connected to lots of different stations and has a high stream of train traffic, then if something goes wrong at that station, that's going to have a much larger effect propagate out on the network. And it's that sort of idea that leads us to think about how we might be able to use this network approach to identify how to intervene in network systems. Before I go on to show some graphs and talk about intervention in a bit more detail, it's probably a useful little point to talk about some network or graph terminology. So in networks, we have nodes and edges. So nodes are the observable variables that we measure. So here we might have fear of novelty or sort of novel object test, hair cortisol, and let's say latency in a judgment bias task. The edges are the lines connecting nodes, and these are typically statistical relationships between variables, nodes, after controlling for everything else you've measured. So they're not marginal correlations, they are conditional associations. Blue normally represents a positive association, red represents negative, and the strength of the association is normally depicted by the thickness of the line and also the color saturation. So here we can see that we've got a minus 0.68 partial correlation. So this line is thicker and more color saturated than the blue line, which is 0.32. Technically, there are lots of different types of network. In this talk, I'll just focus on undirected networks, which means there's no arrowheads. So we don't to encapsulate our uncertainty that we don't know what the direction of that association is. We just know that there's this conditional association present. And it's a sort of network that's typically estimated on sort of cross-sectional data. So measure a large group of individuals at one point in time. And the reason I'm going to focus on this is because for now, that's probably the most realistic application, although probably not the most fruitful for the network approach, but we'll focus on it for now. And so one of the important things to point out about interpreting these networks, so with these three variables here, if I looked at just the marginal correlations, then I would see a correlation between hair cortisol and cognitive bias here. However, because these are conditional associations, so because I can control for this node, that correlation is spurious and it disappears once I do that. So there's no correlation between these, any correlation can be completely explained by this other node here. So it gives us potentially, without going into too much detail, a little bit of a glimpse or a hint of relationships that are more likely to be causal in nature rather than spurious. We can't infer causality, in the strict sense, but it could potentially be interpreted in terms of clues or hints, if you like. You've got to be a little bit careful with how we interpret it. So let's say I want to know how, what I should intervene on to improve shelter dog welfare. So one sort of, if you like, research program that I might do this, I might say, okay, I've got this bunch of measures that are feasibly, their own distinct components. I want to measure it in a large group of dogs and find out what the network structure is to identify what might be important in that system. So let's say we've done that. Now this is simulated data, it's not real, so don't read into the results too much. But let's say, so we've got things here like sort of fear of novelty, appetite, coprophagia, body condition score, fearful posturing around unknown people in the absence of people, aggressive behaviour, repetitive behaviour, kennel activity, and so on. And what this network shows us in particular is that this novelty node here, which is a larger circle, so this is just one way we can sort of present this information, is so here if I sum up all the connections that a node has, and I call that my measure of influence, then the size of the node in this graph represents that. So we can clearly see that this novelty node is much larger than all the others, which would imply it's potentially the most influential. And you can see that it's got lots of connections to pretty much every other measure, and it's got a few quite strong connections. And then there are other variables like this kennel activity node, which has got a few connections, but they're generally weaker, and it's much smaller here. So you can see that there's potentially a big difference in this measure of influence. So maybe this suggests that actually, it's unfeasible for me to maybe implement 14 interventions. So if I was restricted to, let's just say I was restricted to doing one intervention for now, maybe I want to start with, changing dogs' perceptions of novelty. So to present this idea of the centrality hypothesis, we sort of just ran a quick computational simulation of intervening in these systems. And in this network, so we ran two simulations. We ran one simulation where we intervene on the novelty node. So that's represented by the square node here. This means that basically we artificially set that to 0. So we completely cured dogs' perception or fearfulness towards novelty. And in the low centrality intervention, we intervened at a not very influential node. So this kennel activity node down here. So we set that to 0. We completely improved a dog's activity level in the kennel to a much more, what we think is an acceptable level. And in this graph, what you can see is the yellow pie charts that fill each node. They represent the probability that that node is active. So in the high centrality intervention, you can see that there's a huge difference between this network and this network. So in the baseline network, we've got pretty much these welfare measures or nodes are activated all the time. Whereas in this network, we see a huge improvement. There's still some random activation or problems, but generally it's massively improved. If you look at the low centrality intervention, then other than the kennel activity node, which we artificially set to 0, there hasn't been a major change in the rest of the network. The network's still pretty active. If you compare it to that, it looks almost pretty similar. So that's the basic idea. Maybe intervening on important nodes is important. Another hypothesis or aspect of this network approach, which might apply to animal welfare, is the connectivity hypothesis. So in the human literature, this basically states that more strongly connected networks are more vulnerable to symptom spread. And potentially that idea applies in animal welfare too. So if we look at the diagrams here, so in this top diagram, or this top graph, this top mini network, we've got 4 symptoms or 4 welfare measures. And we have sort of connection here, connection here, connection here. And this, think of it as sort of a stressor that can activate the system. In this bottom row, we have the same measures. We have a connection here, connection here, but we have this additional connection here. And the lines are thicker to kind of represent that these direct associations are stronger as well. So this bottom row represents a more strongly connected network compared to the top. Now, in the more weakly connected network that's a bit more resilient, if a stressor appears, it might activate a couple of nodes, a couple of symptoms, a couple of few compromises on a couple of welfare measures. But it won't, because the connections are weak, it doesn't propagate through the whole system. And when that stressor is removed, the system returns to its kind of rested state of deactivation. In a more vulnerable network, which is more strongly connected, however, we see different dynamics. So in this network, the stressor appears, activates the same 2 symptoms, but because the network is more strongly connected, we see it propagates throughout the rest of the network and activates these remaining 2 nodes. Another implication here is that here the stressor is removed, but the network is now in a new stable state. So it's now in a state that is maintaining itself, even though you've removed the stressor. So there's a couple of things that are of interest in the animal welfare context here. One is, can we test this connectivity hypothesis in animal welfare? Does it apply to the measures we have if we're dealing with network systems? If it does, then potentially this is a useful new theoretical way of conceptualizing sort of vulnerability and resilience, but potentially also a new useful measure of animal welfare. If we find evidence to support this hypothesis, and we measure 2 groups, and one group has a more strongly connected network than the other, we might conclude that actually that group's welfare is compromised because they have a more strongly connected network and are at greater risk of ending up in sort of more compromised states. Another potential application is, so the previous 2 examples have talked about sort of once we've estimated the network structure, metrics we can use to summarize the structure of that network or capture some sort of characteristic about the network. However, we might simply be interested in sort of what connections are present in and of themselves. So in this example, again, this is simulated data, so it's not empirical, so don't read too much into the results. But it might be a useful way to sort of systematically identify the effects of stressors on measures of animal welfare. So in this example, let's say this data represented survey data, questionnaire data, and I asked dog owners about seven questions that captured various different aspects of welfare. So sleeping, playfulness, novelty, aggressiveness, stool, appetite, exploratory behaviour. And I also asked them, how much do they agree that they use some form of aversive training to manage their dog's behaviour. I can estimate a network on this data. The blue lines here, when interpreting this, are basically the partial correlations, so these conditional dependence relations that we can be confident of, and the grey lines you see in the background are basically estimates that we're not sure are different from zero, so they may represent conditional independence. And what we could do from this is we could look at it and we could say, okay, well, this aversiveness is strongly related to having a direct effect on animals' ability to sleep and aggressive behavior. As we saw in the previous example, obviously we want to get rid of this aversiveness, the stressor, but just because we do that, it doesn't necessarily mean that the state of the network will improve, because it might be in this stable state. So we need to think about interventions, and it might be, there's a potential here. I'm not saying these ideas are set in stone, but it might be that if we know what the direct effects of stressors are, it might be that it makes sense to intervene at the level of their initial effects, maybe. So here, maybe I decide to, target sleep and aggressiveness and start with that and see what I'm left with, rather than, throw 7 interventions at an owner to affect every single variable I'm looking at. So the kind of take home from this is, maybe knowing the specific direct effects of different stressors may help tailor interventions based on which stressors are present. And it may give us just generally a bit of a better understanding about how various stressors affect different sort of aspects, components of welfare. So on to the first empirical example, which follows the sort of approach just outlined in the last slide. So we use network analysis to identify direct associations between sort of purported painful health conditions and behavior in companion dogs. So we conceptualize pain as an external stressor, which could impact a network of sort of internal behavioral measures. Here, our behavioral measures were individual items in the PANAS owner report psychometric questionnaire. And previous research, so we reanalyzed data that had already been reported, and the previous research that used this data used the sum scores from the PANAS questionnaire. So normally you get a score for positive effect and negative effect. And that research showed that there was a negative or detected a negative association between current painful health condition and the positive effect sum score, with no association detected with the negative effect sum score. What we did was estimate an undirected network model with pain and age as nodes within the network of PANAS items. And essentially the reason we did this was because the network model might be capable of discerning, or it is capable of discerning item level information, from sum score information. So it allows for a slightly more fine-grained level of analysis. It also allows for possible identification of small conditional dependencies with negative effect items that might be obscured once we kind of sum score information away. So the network model also allowed us to distinguish between marginal, so sort of marginal correlations or potentially indirect effects, and conditional, sort of direct effects of pain. So if we do that, we end up with sort of two networks here. And on the left here, we have the marginal correlations that are sort of statistically different from zero. And you can see that actually, pain, there's lots of edges from pain going out to different nodes of both positive effect and negative effect. However, if we look at the conditional network, so in this, with this data, this is partial correlations, which is a type of conditional dependency measure. We see that a lot of these edges with pain disappear, and we're only left with 3. We've got a strong positive relationship between age and pain. Makes sense. We have then 2 negative edges between pain and this negative activation item here, 11, not relaxed, and pain and this positive activation, energy. And the interesting thing is that if we then look at this energy item, we see that it has positive relationships with pretty much every other, except a couple of the items that make up the positive activation sum score measure. So a lot of these indirect edges that you see in this network may well be mediated via this sort of primary direct effect here. So a lot of these additional correlations can be completely explained by the effect that pain has on what owners score their dogs as in terms of energy levels. I want to talk about the not relaxed item in too much detail because we did a bunch of some sensitivity and robustness stuff, and that wasn't a very reliable edge. But this edge between age and pain and energy does seem to be quite reliable. So once we used the network to identify the conditional associations, we then looked at easily interpretable conditional probabilities. So what is the probability that a dog has a painful health condition given I know their score on the variables that were associated with it in the network? So what we've got here is, in this first section, the probability of pain given the dog's age. And we can see that this is sort of increases the older the dog gets. So it goes from about, around about 0 for less than 6 months, and it increases up to about 0.34 over 10 years. And then if we look at the middle section, so this is the probability of pain given I know a dog's score on the energy item. So if they answer 5, strongly agree, so the item is my dog is full of energy, then the probability of a painful health condition was around about 0.08, and this increases up until about 0.32 if they answer strongly disagree to that item. I want to talk about the not relaxed one because, like I say, that was a particularly reliable edge. But also regarding the intervals here, they're not confidence intervals, but they are a measure of uncertainty. So we do see an increase in uncertainty on what this conditional probability will be as we go down in scores on the energy item. So to try and kind of quickly wrap up some future developments, the first point is, this talk has covered the basic theoretical ideas and possible applications, but ultimately a lot of this needs empirical testing. Okay, so we've only presented the foundations of this work. The theory will probably need expanding and adapting, Some problems might be genuinely latent variable systems, others might be networks, some might be, hybrid models, of both. Also, I talked about the centrality hypothesis and the connectivity hypothesis. These ideas need experimental testing before we can say for sure that they are useful and they play out in the real world. And other ideas, as the theories develop, may emerge, which ultimately need empirical testing as well. I also haven't, really talked about directed networks, but when we have time series data, we can estimate directed networks. So we have arrow edges, and these capture, the direction of temporal associations, and in a sense, they do capture better the dynamics processes, which really is what network theory is about. And it also allows to estimate some additional types of network metrics on networks, which capture that dynamic aspect a little bit better. However, it is harder to collect. You need quite intensive data, so it can be potentially expensive and quite intensive to collect. As sensors and big data type methods become a little bit more accessible and common in animal welfare, this might be one area that these sorts of networks can be particularly useful for. And when talking about directed networks from time series data, we can also, when we do that, access individual level information. So we can get networks at the group level, but each individual that we've studied over time can also have their own individual network. And this is important because sometimes the systems we're dealing with, the group average might not accurately reflect an individual's network. So this allows us to study the between and within subject effects and potentially really look at start kind of individualizing things. So this network approach, it might lead to development of new assessment and monitoring tools that have been developed specifically from the network perspective and ideas relating to what makes a valid measure in the network sense. And so the second bullet point I've got here, one possible application is when we start thinking about complex systems, this opens up a whole new kind of realm, if you like, of ideas. So one of the things they're starting to explore in the human literature is this idea of early warning signals that precede critical transition. So if someone is in a fairly healthy psychological state, when they transition, a sudden transition into maybe a psychologically unhealthy state, i.e. via the sudden appearance of lots of symptoms or mental disorder. Sometimes in complex systems, when we see those shifts, there are signals in the data before that shift occurs that predict a sudden shift is about to happen. And they started to look at that, whether these appear in human psychological data. There's some suggestions that it does. If those sort of ideas also apply to animal welfare data, whether early warning signals do exist in animal welfare, I don't know. But if they did, that could potentially be a really powerful tool. So, as an example, if we had automatic monitoring of dogs or cats in shelters, and it turned out that, hey, we did know these early warning signals appeared before we see these sudden shifts in compromises in lots of animal welfare measures, then we could potentially get information and prevent these compromises from happening before they do. We're quite a way off that. I just wanted to mention it because I think it's potentially a really cool area where this network and dynamic thinking can potentially lead us to, in the future, as the ideas develop, it could potentially take us to these new places, those sorts of things. And finally, I just mentioned here briefly, when we start to think about systems and dynamics, it leads us to, thinking about, well, can we can we put down some of these ideas in formal quantitative models that might help us study the complex dynamics of our systems of interest. So essentially, basically, everything I mentioned here are all ways to help us understand, predict, and or control behavioral systems by studying or viewing welfare as a bit of a complex dynamic system. So just some acknowledgements to end with. Many thanks go to my supervisors, Professor Oliver Burman and Dr. Tom Pike, and our collaborators on the pain and PANAS data that I presented, Professor Daniel Mills from University of Lincoln as well, and Dr. Sarah Rini, who is from Sheffield and Lamb. Just a few references here, kind of highlight our paper that's just come out in Animal Welfare that talks about some of these ideas in a little bit more detail, if any of this has interested you, and some references from the human literature. I'm happy to take any questions and I'll do my best to try and answer them. Thanks for listening.
Thanks, Tom, for this extremely helpful and visually illustrated presentation on this topic. I'm just a little bit overwhelmed by all the information. We are happy to get questions, as we mentioned at the very beginning, where you can put them in the chat box, or you can just raise your hand and ask them directly. If there are no questions yet, at least I can't see any in the chat box, I just start with one of my own, and this refers to the very beginning of your presentation, focusing on the general idea that several parameters that might be measuring the potentially latent variable welfare are connected. And I was wondering where you, in your opinion, would put something like the subjective feeling of suffering, for example. So we as humans can state whether or not we suffer, yes or not. This might be more tricky. You need to infer this for animals, but would this be something that could be placed into this network, or would be something like this considered like an epiphenomenon on top of the network?
Yeah, good question, and that's a really hard one to answer because it almost touches upon the big problem of consciousness and subjective states. And what I would say is, so in the human literature, sometimes what they do is, because we can directly access the subjective state, they might have a level of analysis in humans where they go, do you feel sad, or do you feel scared, or do you feel nervous? And those are probably emergent states from some sort of kind of sub-network system. In terms of animal welfare, it's a little bit more tricky, because in a sense, I guess, it almost sounds a bit contradictory to the whole talk, but we are kind of interested in latent variables. If you subscribe to subjective state being the state of interest, then we can't access that. And the things we measure, we want our measures to capture something about subjective state. So what I would say is that, at least for the time being, we almost need to make a bit of a rational, some assumptions and a rational validity argument over why a particular measure captures something about subjective state. So you might appeal to something empirical. So for example, let's say nest building as a measure in a network in, say, mice. You might say, well, I think that's a relevant, valid measure of welfare because there is empirical evidence that shows that they will choose to do it even if they have nests available to them. And therefore, I think it captures something about subjective state. So it's a valid kind of individual component in the network. Maybe as the research and the ideas develop, we might be able to almost layer networks on networks. But for now, I think that we can't necessarily directly incorporate subjective state into the networks. We just have to make some sort of assumption or validity argument that what we're measuring is relevant to subjective state. If that answers the question.
Yeah, I just was really curious on your opinion on these specific parameters. And this also kind of targets a second question you mentioned at the later stage, that there are probably indeed networks, or not networks, but there are systems with latent variables that are actual latent variables. But there might also be hybrid networks with latent variables, but a network system around them. Just to, I try to understand, to get a grasp on how that might look like, or what this might be. Do we have any examples from, for example, the human psychology where this is an established approach, for example?
Yeah, so there are developments that have basically combined latent variable models into networks. So you might estimate a latent variable, and the latent variable is in the network, but it's also like a model within the network. So I'm struggling to think of in the human literature some examples where they've done that yet. I just know there's been some papers where they've discussed that there might be, it's potentially you might have both. I guess the difficult thing is, just like in the network perspective, you have to make an argument that this is a valid, reasonable kind of component of its own. I think we also need to do that if we're invoking latent variables, and go, because latent variables assume that it's the variable that causes the variation in the measures. And I think unless we can justify that, then we shouldn't necessarily be measuring it as a latent variable. But it is certainly something that we could include. It's not something I've thought massively about yet, so I maybe don't have a particularly good example to give you. I just kind of wanted to put it in there, so to just kind of say that, hey, it is possible that we can combine them, but it's not something I've thought about too much yet.
Good, thanks, Tom. I don't see any further questions in the chat. So just dropping a last one by myself, and you just have, you already have the scheme open. You mentioned at some of the other slides that, for example, from the latent variable one, you would target behavior, and you might alter the welfare state of the animal, but you would not expect to have a causal relationship with the other two that you mentioned, like cognition and physiology. So changing one variable, like changing one behavioral parameter, might affect the welfare of the individual, but it wouldn't have an effect on the other parameters that you measure.
Yeah.
But with the arrows as they are right now, welfare would impact on, for example, low appetite and low body condition score. So wouldn't that be a relationship, just with a in-between stop with welfare as a term included, than having an effect on the other parameters as well? Or did I just miss, I don't know, one step that prevents something like this to happen?
Okay, you should still be able to see my slide, don't you? So in this model, basically if we imagine that we can only go in the direction of arrows, so if I tweak this fearful posturing variable, there is no arrow in the model as it stands to any of the other variables. So there's not like an arrow going back to welfare state and then down back to low appetite, for example. So and maybe this is a very strict, if you like, latent variable model. More to just highlight some of the basic ideas. We might not strictly think that, but I thought it's just useful to strip it down to a really strict example to highlight some of the implications, because if we, because these are predictions that we can test quite easily. So, if welfare is this thing, this latent variable that is causing changes in all the things we're measuring, then we should see, systematic correlated changes in everything. Whereas if we're dealing, with, or if that's the case and we only tweak a single thing, then we shouldn't really see much changes to the other measures. So these different predictions can allow us to test some of these ideas in empirical data to get a bit of a better idea about what exactly these structures do look like in reality. Because at the moment, I'm kind of just working with simple, strict structures to get some of the basic ideas in place, and then we can start to maybe expand it out and test some of these ideas, so we get a little bit of a better idea of what do these graphs actually look like in welfare.
Thanks, Tom. I'm still not seeing any questions in the chat or any hands raised. I assume myself that most people are still ruminating about the general construct and think about the consequences and the potential applications on this. So if there are no questions put in the chat or any raised hands, I will just say thank you again to you, Tom, for presenting this approach. It was really, really interesting talk. I think it gave a lot of food for thought for many, many people on the webinar. So thank you so much for presenting this. And thanks to the audience for attending today's webinar. And we will hopefully see many of you in our next webinar on December 6th again. We again will send out a registration link, so feel free to visit the Select workspace or check out the social media or Facebook pages. So thanks again for joining, and thanks again, Tom, for presenting.
No problem. Thanks for having me.